Hey everyone, let's talk about the theory of multi-conductor transmission lines. So I've kind of drawn a crude schematic for a three-conductor transmission line, but the basic derivation here can actually be extended out to any arbitrary number of lines. So you're probably familiar by now, I hope, with the traditional theory of a two-conductor transmission line. So you imagine just kind of ignoring this bottom segment here, where we had a signal line and we had a ground reference here. Okay, and we just did this is the lumped element model, you remember. So you would apply Kirchhoff's voltage law and current law at these various nodes, and you would eventually uncover two coupled partial differential equations, which were the famous telegrapher equations. So when it comes to multi-conductor transmission lines, we're just going to do exactly the same thing, but with a few added terms in our lumped element model. So you remember, for the usual lumped element model, you had a voltage coming in at some node, say z sub n here, or this is position z sub n, and then over here is the location z sub n plus 1, and there's a distance of delta z between them. We also had some conductance between the signal line and ground. There was a little capacitance here. Then you had a series resistance and a series inductance. For the multi-conductor line, you do kind of the same thing on the second line, where there is now some conductance between the second signal line and ground. There is some capacitance. There's a series resistance and a series inductance. And we've denoted these as, say, G22, R22, L22 versus 1, up here for the first line. You notice also we've added a couple of extra terms here. In particular, there is going to be potentially some conductance between signal line 1 and signal line 2. So you see how this is connecting the two signal lines and hopping over the ground. So we call that G12 for the conductance between line 1 and line 2. There's also some capacitance here, this coupling capacitance between signal line 1 and 2, which we denote with C12. And you see how it's connecting them and just kind of hopping over the ground here. And then over here, there is some mutual inductance here, which we denote with L12. And you notice it's kind of like the transformer notation here, right? So the mathematics of that you've probably been exposed to a long time ago, but most circuit classes don't do too much treatment on that, but it is pretty straightforward to model. You see here in green, I've also got some current coming in here to signal line 1, so that's I1. And here is this current on line 2, so that's I2 at Z sub n. And sorry, I had to smush that in a little bit. And then you see I1 at Z sub n plus 1. So there's a current entering here and a current leaving. And the same idea here, there's a current entering and a current leaving. Okay, so that's just the lumped element model for a multi-conductor transmission line. And in this case, we're just going to do a three-conductor line. And like I said, this derivation it can be generalized to just n arbitrary lines, but just kind of for the sake of simplicity, we're just going to do it for a three-conductor line. Okay, so the basic derivation is very straightforward. All we're going to do is apply Kirchhoff's voltage and Kirchhoff's current law, right? So you have KVL and KCL. So let's go ahead and do Kirchhoff's voltage law right now. So KVL. All we're going to do is just say here is voltage V1 minus voltage there's V1 at Z sub n plus 1 and V1 at Z sub n. So what we're going to write is the following. V sub 1 at Z sub n plus 1 minus V sub 1 at Z sub n. So that is the voltage drop from here to here. So that voltage drop is going to simply be a function of the current that flows through this resistor here and this inductor, right? Because you notice this voltage here is constant across this entire node. So basically, it is just this little voltage drop from there to there. So the voltage difference from here to here. So I've actually written this backwards here. So I want my current to go this way. So that means I want this voltage to be higher than this one here. So what I'm actually going to do is cross this out. We'll say V1 at Z sub n minus V1 at Z sub n plus 1. So you imagine the current going this way, meaning this is the higher voltage and this is the lower here. And that voltage drop is just going to follow Ohm's law here. So I'm going to have this current, I1, and it's going to be at Z sub n plus 1. Now, keeping track of these positions is going to get a little tedious, so I'm just going to kind of stop writing down the actual position. It's going to be pretty strongly implied from the context. And we're going to do kind of that limit as this approaches 0 anyway, so it's not going to matter too much. So I'm just going to say I1 here times R11. And then there's a voltage drop through this inductor, so that's going to be plus I1 times L11 di1 dt. And remember also, just you got to keep in mind, these are all per unit length parameters here. So technically, I need to put a delta z and a delta z on all of these terms. However, we're going to divide that out momentarily anyway, so we might as well just cut to that chase like that, right? So you do this, remember we did this before with the lumped element parameters for a two-conductor line anyway. And technically I should probably put primes on these to indicate per unit length, but there's not much point in doing that in the extended notation here. And then finally, we also have to account for the fact that there's a mutual inductance here. So what that means is a current over here is going to also induce a voltage over here on this inductor like a transformer. So I'm going to write plus L12 times di2 dt like that. So sorry, it's a little messy. So that was nothing. We just aren't writing that down there. And the delta z's have been divided out here. So this is pretty straightforward. And what we're going to do is just take the limit as delta z approaches 0, just like we did before. So I'm kind of going a little quickly here, but that just means this little term here on the left is going to turn into a derivative. And in particular, though, the finite difference is backwards. So I have to put a minus sign here. So you get negative dv1 dz is equal to, and then we'll just kind of write this stuff out here. I'm going to get I1 times R11 plus I made a mistake here. This should be, excuse me, L11 di1 dt. So sorry about that. And then I'll get a plus L12 di2 dt here. So that's a little more cleaned up. And then by a similar argument, you do the same thing on line number 2 here, and you'll find that negative dv2 with respect to z is going to give me I2 R22 plus L22 di2 dt plus L21 di1 dt. So you have this idea of there's a voltage drop from here to here, and current changing up here is going to create sort of an EMF, an induced voltage over here, which is represented by this term. And by reciprocity, we also know that L12 is equal to L21. Okay, so that is a fundamental property of just transformers in general here. Okay, so I have two differential equations here representing the changes in voltage here and here as a function of the currents everywhere. Now, it turns out we can simplify this notation tremendously by writing something like the following. I'm going to define a vector v as simply v1 of z sub n, or sorry, z comma t, and v2 of z comma t, like that. So it's a vector of voltages along this line. And then there's going to be a current, so I'm using a little arrow here to indicate that that is also a vector. And it's going to be I1 of z comma t, and then I'll have an I2 of z comma t, like that. And then I'm going to define my resistance matrix, which is going to be R11, 0, 0, R22. And then we're going to need an inductance matrix, finally, so L matrix. So we'll write that here. Is going to look like this: L11, L12, L21, L22, like that. So I'm going to plug in all these little substitutions. I'm going to get something that looks like the following: negative partial with respect to z of my vector v, my voltage vector, is equal to, I'm going to have R matrix times my current vector plus my L matrix times the time derivative of my currents, like that. So that should look pretty familiar, okay? So we'll just put a little box around this guy and save it for later. So now what we're going to do, that was just Kirchhoff's voltage law here, applied to the voltage drop here and here. And again, sorry, I got a little scribbly, but hopefully that was pretty straightforward to follow along. So what we're going to do now is just apply Kirchhoff's current law. All right, so what you do is you look in here. There's going to be a current into this node and a current leaving it. And we're just going to kind of apply a certain conservation of charge, right? Because there's going to be a current in, and there's going to be some current leaving here, 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 and here, and here. And I just have to add them all up to get 0. So I'm just going to kind of put this over here on the side so we can keep track of it. So we'll have Kirchhoff's current law. And I'm just going to have my current in is equal to my current out. So I1 at Z sub n is going to equal... So I have this little term here. So there's going to be a little current leaving, jumping from signal 1 to signal 2. So it's going to be G12 times V1 minus V2. Okay, because you can imagine here is some voltage drop with a current going through that resistor there, or that conductance. Then there'll be this term here. So I'll say plus G11 times V1. So that's just with respect to ground there. And then we'll have this capacitor here. So let's see, we'll move this kind of off to the side. And then I'll have plus C11 dV1 dt. And then the final term is going to be this guy. Well, second to last, I'm going to have a current jumping from line 1 to line 2 through this capacitance. So what that turns into is plus C12 times the time derivative of V1 minus V2. Okay, so that's the delta V between signal line 1 and signal line 2. And then finally, there's this current that's going to come out the other side. So plus I1 at Z sub n plus 1. Or you could think of it as Z plus delta Z, right? So what we're going to do is oh, and of course, don't forget, technically these are all delta Z's on everything, okay? So I always forget that little term. So there's a delta Z on that, right? Because these are per unit length parameters here. What we're going to do is subtract and divide that delta Z out anyway. So what you'll get is this, negative I1 at Z sub n plus 1 minus I1 at Z sub n divided by delta Z. So I've just divided all those little delta Z's out anyway. And then that will equal the following. So you got to be a little careful now. So we're going to rearrange my terms a bit. So I'm going to get G11 plus G12 times V1. Okay, so and then so you see these terms come together. And then we can get another something over here, minus G12 V2. And then I'm going to get plus C11. Now you got to be a little careful here. So I have some like terms. So it can be C11 plus C12 times dV1 dt. And then finally, there'll be one last term minus C12 dV2 dt. Okay, so I just rewrote these terms a little bit into a more manageable form. So again, we're going to do the limit as delta Z approaches 0. And that's only going to affect this left term here. So I'll get negative partial I1 with respect to Z is equal to all of that. All right. So let's just go ahead and I don't have to rewrite it again. So by a similar argument, though, we do the same thing on the bottom line, right? So there'll be a current in, leaving all those, and you add them all up, and you get a very, very similar expression. So I'll just put a little dot, dot, dot. It's just that. So then I'll get negative partial I2 with respect to Z is equal to, and let's double check the notes here, just because it's easy to make little mistakes. So you get, so there'll be a, let's see, G22 plus G21, so that's a G, times V2 minus G21 V1. So the 2's and the 1's get flip-flopped. And then I get a plus C22 plus C21 times dV2 dt minus C21 dV1 dt. Right? Now, as you see exactly the same thing, you just flip-flop the 2 for the 1 when you're doing the second signal line. All right, so what you then notice is I have some interesting parallels here. It looks a lot kind of like that. So I can rewrite this term here on the left. That's negative partial with respect to z of my I vector, right? Because this is a system of equations. So we're just going to use a matrix vector notation to write it out. And let's see. So this becomes G times V and plus C times dV dt, like that. So if we put that back up into here, I'm just going to rewrite this. Partial with, with respect to z of I is equal to GV plus C dV dt, like that. So I'm going to put a box around that. So the only difference here now is these two matrices are a little bit differently defined. So my G matrix looks like this. I get a G11 plus G12, like that. That's my first element. And then there'll be a negative G12. And then I get a negative G21, but they're identical. So that's, we can just make a little note here. G21 is equal to G12. And then I'll get a G22 plus G21 down here. Okay, so the form of this matrix is a little less intuitive than it was in the previous case. And then for my capacitance matrix, it does something very similar here. Okay, so I will get a C11 plus C12 minus C12 minus C21, and then there'll be a C22 plus C21, like that. And again, C12 is equal to C21. Okay, so what happens is if you extend this out to n arbitrary transmission lines, you have to add up, the diagonal term will be a summation of all of these guys, and the off diagonals get these negative signs here. Okay, but that's a pretty straightforward derivation for the multi-conductor transmission line equations. And they all end up with this general form here. So you can think of this as the general multi-conductor telegrapher equations, right? So I'll write that. Telegrapher equations, okay? For multi-conductors, right? Or you can call it just the multi-conductor transmission line equations. But you notice they share exactly the same form as we had before with the telegrapher equations for a two-conductor line. You just start extending out and you get this sort of matrix vector notation, where again, you have these coupled partial differential equations, and you just have vectors for your V, and you have these resistance, inductance, and capacitance, and conductance matrices. Okay, so that is essentially everything you need to know about the theory of multi-conductor transmission lines in terms of like the foundational governing equations, and everything just kind of falls out of this from here. So, for example, if I wanted to add a source to this, you could just, throw it in, just plus minus, and you would add that into your Kirchhoff's voltage laws, right? And I'd put some output impedance there, say. And you can start adding sources here. And you can even add maybe a differential source like this, right? So I can excite two lines relative to each other or relative to ground and that sort of thing. And you would just throw those into these equations here. You can even do finite difference time domain simulation using exactly the same methods as before, where these partial derivatives are turned into finite difference equations. And then you solve that, rearrange them to solve for like the future term, and you do that kind of leapfrogging step, just like you did in lab number 1. It's the exact same idea. There's just more terms you have to keep track of. Okay, and this is actually a very rich theory unto itself that has a lot of interesting practical applications, because now you can account for multiple conductors, not just as transmission lines, but they'll have coupling relative to each other, which is what we saw with the coupled line coupler. Okay, so that is a really interesting field. There are whole textbooks written about this, and some of you may need to be familiar with this and explore it if you're going on to some of your graduate level research. Okay, but you can see the basic idea, nothing really new happened. We just did the same sort of lumped element derivation with Kirchhoff's voltage law and current law. We just accounted for more terms. Okay, so again, don't let the notation here fool you. It's just a nice compact way of accounting for all of my voltages and currents here in this neat matrix vector notation.